Here's a concept map that I've created to help me summarize this week's key concepts and ideas, and review the chapter with you now that you have completed your own collaborative online concept map with the others from your small group. As you can see, I've included the title of the chapter, Confidence Intervals, near the top of my concept map and slightly to the left. It's been highlighted, and in this case I used a slightly larger font and color to differentiate it from other nodes in my concept map. Last, I think it might be warranted to make a comment on the aesthetic feel of my concept map. I've used colors to denote clusters of ideas, coherent ideas that fit together, but I've also used colors and particular kinds of lines, for example, dashed lines and dotted lines, to create a sense of parallel structures. I will say a bit more about that as we proceed through this concept map reading. Aside from the previous concept map, which introduces a number of key and important ideas for the remaining part of the text, this particular chapter introduces us to some initial ideas that properly fall under the umbrella of inferential statistics. In other words, we are going to use characteristics from samples to make an inference about the corresponding population. So, to begin, let's turn to the left-hand side of our concept map. Confidence intervals are used to make claims about populations. So, for example, we might be interested in, say, the population mean, or we might be interested in a certain population proportion, or some other characteristic about the population itself. Of course, this isn't always possible, and so we must rely upon a sample. And so, when we're constructing confidence intervals for some characteristic of a population, we are basing this upon a method that necessarily takes into consideration sampling error. For us to construct a confidence interval, we have to start with a sample mean or sample proportion or whatever characteristic we're interested in as a starting point for the construction of the interval itself. The interval entails constructing an upper and a lower limit around the particular characteristic of the sample that we're interested in. Creating this upper and lower limit allows us to create a bit of a cushion around the sample mean or the sample portion, whatever we're looking at. And as such, this upper and lower value or upper and lower limit provide us with an interval of values that we believe includes what the actual population value of interest really is. For our purposes here, we are only going to focus on constructing confidence intervals for a population mean and a population parameter, although we can, as noted earlier, construct confidence intervals for a number of other characteristics. Either way, we do need to know some other information, and that in particular is whether or not the standard deviation for the population is known or not. So let's say we're interested in creating a confidence interval for a population parameter. Again, it'll be the mean or the proportion, and we happen to know the standard deviation for the population. Here's where I've split my concept map into two parts. One to follow the process for constructing a confidence interval for the mean, and the other for constructing the confidence interval for a proportion. In the case of a mean, we're interested in using a particular formula, and so the confidence interval is defined by, it's a formula, it's defined by the sample mean plus or minus the z value times the standard error of the mean, or SEM. In the case of a proportion, our construction of the confidence interval is determined by the sample proportion value plus or minus the z value times the standard error of the proportion, or SEP. In both cases, we need to identify the value for our z in both formulas. The z is the value associated with our level of confidence. That is to say, our confidence in that the population mean or population proportion will fall at some point within our confidence interval. So we may choose a value of z. We may either choose a z of 1.96 if we wish to construct a confidence interval which is equal to 95%, or we would choose a Z value of 2.58 for a 99% confidence interval. It is not always possible that we would happen to know the standard deviation for our population, and so we must approach the construction of the confidence interval a little differently. All the same, the approach is similar depending upon whether or not we're constructing a confidence interval for the mean or a confidence interval for a proportion. In the case of a mean, where we want to construct a confidence interval for the mean and the standard deviation for the population is unknown, we would modify our formula ever so slightly, so that the confidence interval is equal to the sample mean plus or minus t times the standard error of the mean. In the case of proportion, our confidence interval is constructed as being the sample proportion plus or minus t times SEP, or the standard error of the proportion. So what is this t thing? Our value for t will come from a t distribution table, and in the case of your textbook, this table can be found in the back in one of the appendices. In effect, we need to use the t distribution table because we do not know if our population distribution is known to be normal. If we knew something about the standard deviation of the population, then we might be in a position to comment on the shape of the population distribution, but we're not. To use the t distribution table, we need to know two things. We need to know 1, the sample size, and 2, the degrees of freedom. And in this case, with this particular test, the degrees of freedom is equal to n minus 1, where n is the size of our sample. The nice thing about this is if our value of t is particularly large, then we can turn to our z-table distribution. In other words, if we were to construct a 95% confidence interval and t is large enough, then we could choose a value of t equal to 1.96. This is just the z value when we're constructing a 95% confidence interval where the standard deviation of the population is known. Similarly, if our t value is particularly large and we wish to construct a 99% confidence interval, we can use a value of 2.58 as our value of t. And this ends my reading of my concept map for confidence intervals.